Hello and welcome. Today we'll be doing differentiation under the integral sign, and we'll be looking at the integral of sine x over x dx from 0 to infinity. And let us note the following now, because of course normally in this kind of work we'll introduce a parameter, let's call it k, and of course at first glance this sounds like a good idea. So we introduce the parameter inside the sign, and then we differentiate both sides of this equation with respect to the parameter, of course. And let's see what happens. There's a little bit of space so I can move it, so I can save myself a line. So I can move that now inside. I can interchange differentiation and integration. I'm using partial, obviously, once I'm inside the integral. Let's rub that off. Differentiating that with respect to k will produce a x coming to the front. The sign will become, of course, the cos of kx over x. The x's will cancel, but now we have a problem. The resulting integral does not converge. I mean, think about the graph of cos, the cos of kx, where k is a parameter, not to infinity. There's no finite answer to that. You got to excuse me. Okay, so what do we do with this integral in order to evaluate it? Okay, we need to introduce a parameter. However, it is not suitable to actually put this parameter inside the sign. So it's this first time we see something like this. We're going to introduce, before we introduce the parameter, a scaling factor or a reducing factor. Often in high-level mathematics, it's a place where we have to do something like that. So we're going to call I of k, where k is a parameter, this particular integral. So this is, of course, what we're trying to find, the sine of x over x dx. And now we need a reducing factor. And this reducing factor is e to the minus kx. Now, let us note that we will get our integral if we put k is equal to 0. But this now has some, when we do the differentiation, will allow the resulting integral to converge. So we continue. As per usual, we're differentiating both sides with respect to k. This time I'm going to interchange differentiation and integration in one. So I'm going to move the differential operator d by dk inside the integral. And in fact, this bit here is independent of k. So I can put it just times if you want, or at the front. It doesn't make a difference. dx. And this will now create something desirable, because of course the differentiation of that with respect to k is going to create a minus x e to the minus kx sine x over x. The x's will cancel, and we have the integral. I'll have a minus, so I'm going to reverse the limits to allow for this minus so I don't lose it somewhere along the workings. E to the minus kx sine x dx. And for those who know me, this is one of the integrals that I really dislike. It keeps coming annoyingly a lot of the time now in this differentiation and the integral sign. I'm sure there's a conspiracy in there. So how are we going to integrate that? I'm going to use complex numbers on this occasion. So I'm going to say that this is the imaginary part, not rather infinity to 0 rather, e to the minus kx. and this is going to be e to the I x dx equal imaginary part infinity to 0. That looks like an 8 e to the minus k plus I lots of x dx. We carry the integration now. Imaginary part. This bracket will double up as the argument of the im and also the evaluation brackets to put limits. Okay, so I'm going to say this is 1 over minus k plus I e to the minus k plus I x between the limits of infinity and 0. I'm not quite sure if all of us can see what's going to happen when we put those limits in there. When we put, of course, k is equal to, sorry, okay, x is equal to 0, we're going to get just that bit at the front. And if we put infinity for our x, if we let x tend to infinity, the fact that we got a minus k on the real part, the I makes no difference really. It will take us to 0. But if we can't see that, let's put the extra line. What I'm going to do is I'm going to switch into sines and cosines so we can all be happy about what I'm doing in there. And let's conjugate that as well at the same time. Minus k minus I. And we got k squared plus 1. That's this bit here. I'm going to go back. So it's going to be e to the minus kx. E to the minus kx. And e to the ix, I'm going to write it as cos x plus I sine x. And with the limits infinity and 0. And now we can see better what's happening in there. If we put 0, what's going to happen there? First of all, e to the 0 is 1. Cos of 0 is 1. This is gone. So all of this is 1. So the only thing that survives is this. So we go imaginary part minus k minus I, k squared plus 1. And if we let x tend to infinity, so what's going to happen now? If x goes to infinity, this will be finite, okay? However, this will go to 0. So all of this thing will go to 0, taking along this bit here as well. So that's the only thing that will survive. And now we just need the imaginary part of that. And the imaginary part of that is going to be minus 1 over k squared plus 1. So we found that di by dk is just this quantity here. So let's lose all these workings, the in-between workings. And write it here. And then we'll reverse our steps. And hopefully we'll get our answer very, very soon. And very, very quickly. So that's going to be minus 1 over k squared plus 1. And now we're after the I of k. So integrating both sides. This is just an arctan, so it's going to be minus the arctan of k plus some constant c. Okay. So let's see what this means. This means the I of k. So let me just write it better perhaps. I of k is equal to that. And what's I of k? This. So let's write in its full glory. E to the minus kx sine x over x dx is equal to constant minus the arctan of k. So now we need to pick a suitable value for k in order to evaluate our constant of integration. And the only sensible value of k that will allow us to do that is not a finite value. Let k tend to infinity. I don't want to write equal to infinity. If we let k goes to infinity, nothing to do with this infinity. This infinity is in x. We let k is equal to infinity. this will produce a zero integrand. So the left-hand side will become 0 is equal to constant minus the arctan of infinity, positive infinity, is pi over 2. So we're going to get, therefore, the constant is pi over 2. I don't know why I didn't write there. Didn't like that part of the board. And therefore, let's see what we got so far. I think we're done now. I of k is, of course, we got the I of k as equal to, I want to put that first, pi over 2 minus the arctan of k. So in other words, the integral from 0 to infinity, because that's of course my I of k, e to the minus kx sine of x over x dx is in fact pi over 2 minus the arctan of k. I'm after, of course, the integral not to infinity sine of x over x. And of course, I can get that if I let k is equal to 0. So if k is equal to 0 now, I'm going to get not to infinity, that's going to be 1 now, sine of x over x dx is equal to pi over 2. The arctan of 0 is 0, and therefore the desired answer has been obtained. And I hope you have followed this. This is actually not hard at all, this particular one, apart from the fact that we need to know that, of course, we need to introduce that initial factor in the very beginning. Okay, I'm signing out, and I will be with you for another lecture real soon. Bye for now.